Hi everyone, my name is Patricia Montes and I am presenting this week's chapter 14, which is Developing Fraction Concepts. We are going to start off with the learning outcomes, which is describe and give examples for fractions, constructs, and fraction models, explain foundational concepts of fractional parts, including iteration and partitioning, illustrate the concept of equivalence across fraction models, and describe strategies for comparing fractions and ways to teach this topic conceptually. So we are going to start off with a quote, which is, "Fractions are one of the most important topics students need to understand to be successful in algebra and beyond, yet it is an area in which U.S. students, as well as students in many countries, struggle." So we are starting off with the meanings of fractions. There are several definitions and meanings of fractions. I would say it depends on what grade you're in. For example, in the Common Core State Standards, students partition shapes and refer to the fractional amounts in grades 1 and 2 as equal shares. In grade 3, fractions are a major emphasis with attention to using fraction symbols, exploring unit fractions, and comparing fractions. By grade 4, they start focusing on equivalence and begin working on fraction operations. The chapter does mention that fractions have numerous constructs and can be represented as areas, quantities, or on a number line. And this is the section that we're going to be talking about, and I'm going to be describing those next. So now we move on to the part whole, and I have an example here on the right. Using the part whole construct is an effective starting point for building meanings of fractions. I know we've all seen it before. Part whole can be shading a region, part of a group of people, such as 3/4 of a class went to the science museum, or part of a length like Susie walked 3.5 miles. So it just depends what context you are using on that. And then for division, as with whole numbers, it means sharing into equal sized groups. So I can give you a quick example. 4 friends are sharing 8 slices of pizza. Let's make sure each friend gets the same amount. How many slices of pizza will each friend get? Students can determine how many slices of pizza each friend will get and should feel comfortable being able to represent that quantity as division and as fractions. We now move on to measurement. Measurement involves identifying a length and then using that length as a measurement unit to determine the length of a specific object. So for example, let's think of the fraction 6/8. You would use the unit fraction 1/8 as the unit and then count or measure to show that it takes 6 of those units to reach 6/8. In other words, 6/8 is thought of as 6 times 1/8. So then students will be able to see fractions as multiples of unit fractions. The next one is ratio. So the ratio is used to express the relative size of 2 or more values. Similarly, the fraction defines the parts of the whole. On the bottom, you can see the different ways it can be expressed. And the next one is operator. Fraction is operator built on the concept of seeing a fraction as a multiple of a unit fraction. Fractions can be used to indicate an operation, as in 4/5 of 20 square feet or 2/3 of an audience. These situations indicate a fraction of a whole number, and students may be able to use mental math to determine the answer. But it was mentioned that this construct is not emphasized as much in school. Now we move on to fraction language and notation. The way we write fractions with a top and a bottom number and a bar in between is a convention, one that can be difficult for young students to understand. Fraction instruction should begin with the use of the words, like for example, 1/4. On the slide, you could see the words 1/4 rather than the symbols, which is the numbers. In doing so, students will first focus on making sense of fractions as a part instead of making sense of the symbols. On this next slide, I added some examples that the chapter had on how to pose questions to make sense of symbols. For example, what does the numerator in a fraction tell us? What does the denominator in a fraction tell us? What might a fraction equal to 1 look like? How do you know if a fraction is greater than or less than 1, greater than or less than 2? I think such questions can help them build that knowledge on what fractions actually are and making that connection with the symbols and the words of what fractions are. Fraction size is relative. A fraction by itself does not describe the size of the whole. A fraction tells us only about the relationship between the part and the whole. So think for a second, if you were told that you had the choice to choose a third of a pizza and a half of a pizza, which one would you pick? A person who would not know the actual size of the pizzas would typically pick the half, because the half, in your head would be more. But in this case, you would end up with a small piece of pizza because you did not consider the size of the pizza. You did not consider the size of the whole. So now we move on to area models. Fractions are determined based on how a part of a region or area relates to the whole area or region. Then there's length models. Fractions are represented as a subdivision of a length of a paper strip, for example, or as a length distance between 0 and a point on a number line, subdivided in relation to a given whole unit. And then the next one is set model. Fractions are determined based on how many discrete items are in the whole set and how many items are in the part. I think for me, set model would be very helpful for students who struggle with fractions. And I think, for example, you can have Legos, you can have them split Legos apart and compare fractions and see if that hands-on learning will be helpful for students who are struggling with learning this concept. And then on these next few slides, I had examples and pictures of models for fractions that were used in the book. This first slide, it's for area models. You have circular pie pieces, rectangular regions, forts on the Geo-board, paper folding, pattern blocks, drawing on grids or dot paper. On this next slide, on the left, you have the length models. So measurement tools like number lines and rulers, fraction strips or folded paper strips. And this one on the right, they're examples of set models that you can use. You can use counters, or you can use actual objects to show fractions. One little misconception with set models is that students focus on the size of a subset rather than the number of equal sets in the whole. So you gotta be careful with that. Before we move on to the next slide, I just wanted to add a bit of a note. The chapter did have links to several different websites that you can use for your students to understand fractions better, so I would definitely look back at those. They're like virtual manipulatives, and they're available with all three models, so I would definitely recommend checking those out. Now we move on to fractions as numbers. The first goal in the development of fractions should be to help students construct the idea of fractional parts of the whole, the parts that result when the whole or unit has been partitioned into equal-sized portions or fair shares. One of the most important ideas for students to develop about fractions is the sense that fractions are numbers, quantities that have values. You may not be familiar with the terms partitioning, which means splitting equally, and iterating, which means counting a repeated amount, but as you will see, they connect to whole number concepts you will recognize. Partitioning is sectioning a shape into equal-sized parts. When, for example, a brownie has been partitioned into 4 equal shares, the parts are called fourths. On the slide, I have examples of a worksheet where students are partitioning into 2 equal shares or 4 equal shares, and you could see that there. The chapter does mention that students often see illustrations of fractions where they are already partitioned into equal shares. For area models, those groups tend to also be the same shape. This results in students not noticing the critical feature of fractional parts. So I would try and have students practice partitioning into equal shares, and then later on moving on to illustrations of fractions that have already been partitioned. On this next slide, I have partitioning across fraction models. Here I have area models that are typically used to partition. You have pattern blocks, counters, and rods. Area models are the first types of models to use in teaching fractional parts. When partitioning an area into fractional parts, students need to be aware that the fractional parts must be the same size, though they don't have to be the same shape, and the number of equal-sized parts that can be partitioned within the unit determines the fractional amount. It is also important for students to understand that sometimes visuals do not show all the partitions, For example, like the picture that I have here on the right. The next concept we'll be talking about is iterating. In whole number learning, counting proceeds and helps students to add and later subtract. This is also true with fractions. Counting fractional parts or iterating helps students understand the relationship between the parts and the whole, and to understand a fraction as a number. After experiences iterating, students should be able to answer the question, how many fifths are in one whole? Just as they know how many ones are in 10. So the main purpose of iterating activities is for students to develop that measurement interpretation of fractions. Iterating can be done concretely by using a single piece representing one unit or one share and repeating it a number of times to measure how many are in the whole. While equal shares can be found by partitioning, estimating one share and seeing if it is accurate builds understanding of the relative size of unit fractions. Iterating makes sense with length models because iterating is like measuring, and the number line is a good model for iterating with mixed numbers. But iterating can also be done with area models, for example, like the circular fractional pieces. You can use the context of quesadillas, for example, or engage students in creating their own fractional pieces using paper plates of different colors and use those plate pieces to build various fractional amounts. Magnitude of fractions. Number sense of fractions requires that students have some intuitive feel of the size or magnitude of fractions. This requires that students see a fraction as a number, which helps them develop that fraction sense. The use of context, models, and mental imagery can help students build a strong understanding of the relative size of fractions. So we now move on to talk about equivalent fractions. The book did mention that equivalence is a critical but often poorly understood concept. Fraction equivalence and comparisons are emphasized in grade 3 and applied in grade 4, and so on, as students engaged in computation with fractions. Students cannot be successful in fraction computation without a strong understanding of fraction equivalence. So fraction equivalence is that base that students need. To help students build a strong and flexible understanding of equivalent fractions requires the use of many contexts and models in which the goal is to rename a fractional amount. This is the first time in students' experience that they are seeing that a fixed quantity can have more than one name. Area models are a good place to begin understanding equivalence. And here you can see the different area models that you can use to introduce that concept. Length models are also important to develop an understanding of equivalent fractions. Asking students, for example, to locate 2/5 and 4/10 on a number line, for example, can help them see that the two fractions are equivalent, but the line is partitioned differently. Fractions greater than 1. Students must be able to move flexibly between fractions greater than 1, for example, 13/6, and mixed numbers like 2 and 1/6. If students have counted fractional parts beyond one whole, they know how to write the 13/6. And if you have encouraged them to also tell how many wholes they have counted, they will also know this is equivalent to 2 and 1/6. Connecting cubes are very effective in showing how fractions greater than 1 can be written as whole numbers or mixed numbers as well, which is why I put that picture there of 12/5 and 2 and 2/5. Once students have gotten that practice, you can help them move from that physical model to mental images. Challenge the students to figure out the two equivalent forms by just picturing the stacks in their head. Once the students understand that fractions can have different but equivalent names, they are ready to develop a method for finding equivalent names for a particular value. An area model is a good visual for connecting the concept of equivalence to the standard algorithm for finding equivalent fractions. Multiply both the top and the bottom numbers by the same number to get an equivalent fraction. Ask students to look for a pattern in the way that the fractional parts in both the part and the whole are counted. On the picture here below, it's an example of garden plots. So you can have students draw a square or a garden on blank paper, or give each student a square paper like origami paper. And you can start explaining that the garden is divided into rows of various vegetables. In the first example, you might illustrate 4 rows and designate 3/4 as corn. Ask students to partition their square into 4 rows and shade 3/4 like the figure that I have on here. Then explain that the garden is going to be shared with family and friends in a way that each person gets a harvest that is 3/4 corn. Show how the garden can be partitioned horizontally to represent two people sharing eighths. Ask what fraction of the newly divided garden is corn, which is 6/8. Next, tell the students to illustrate ways that more friends can share the garden. They can choose how many friends, or you as a teacher can. For each newly divided garden, ask students to record what fraction of the garden is corn using a table, equations, or even both. Writing fractions in simplest terms. To write a fraction in simplest terms means to write it so that the numerator and denominator have no common whole number factors. One meaningful approach to this task of finding simplest terms is to reverse the earlier process, as illustrated on the picture down below. The search for a common factor or a simplified fraction should be connected to grouping. Two additional things should be noted regarding fraction simplifications. Notice that the phrase reducing fractions is not used, because this would imply that the fraction is being made smaller. This terminology should be avoided. Fractions are simplified, not reduced. Also, do not tell students that fraction answers are incorrect, if not in the simplest or lowest terms. This also works against understanding equivalence. Comparing fractions. When students are looking to see whether two or more fractions are equivalent, they are comparing them. If they are not equivalent, then students can determine which ones are smaller and which ones are larger. The comparison question to ask typically is, which of the following two or more fractions is greater, or are they equal? You can point out that this question leaves open the possibility that two fractions that may look different can in fact be equal. Comparing fractions using number sense. For 8th graders, only 41% were able to correctly put in order three fractions given in simplified form. This builds a strong case for the need to teach students number sense strategies to compare fractions. You can start off by using context. For example, circles. Circles are a popular fraction tool, and because sharing brings to mind food, many contexts end up being about brownies, cookies, and pizza. Using a more expansive collection of contexts helps students see fractions in their world. Additionally, because a number line is one-dimensional, it can make comparisons more visible as well. Now we move on to comparing unit fractions. A student can often think 7 is more than 4, so sevenths should be bigger than fourths. The inverse relationship between number of parts and size of parts cannot be told, but must be developed in each student through many experiences, including the ones described earlier, like partitioning, iterating, equivalence, and magnitude of fractions. Comparing any fractions. You have probably learned specific algorithms for comparing two fractions, such as finding a common denominators or using cross multiplication. Too often, these procedures are done with no thought about the size of the fractions, and often they are not the most efficient strategy. If students are taught these rules before they have had the opportunity to think about the relative sizes of various fractions, they are less likely to develop number sense or fluency to effectively compare fractions. In conclusion, here are some teaching considerations for fraction concepts that the chapter had. Because the teaching of fractions is so important, and because fractions are often not well understood even by adults, a recap of the big ideas as well as challenges with fractions is definitely needed. Many of these strategies may not have been part of your own learning experiences, but they must be part of your teaching experience so that your students can fully understand fractions and be successful in algebra and beyond. Iterating and partitioning must be a significant aspect of fraction instruction. Equivalence, including comparisons, is a central idea for which students must have sound understanding and skill. Research-based recommendations that provide an effective summary of this chapter give a great emphasis to number sense and the meaning of fractions rather than rote procedures for manipulating them, provide a variety of models and contexts to represent fractions, emphasize that fractions are numbers, making extensive use of number lines in representing fractions, spend whatever time is needed for students to understand equivalencies, including flexible naming of fractions, link fractions to key benchmarks, and encourage estimation. And that concludes my Chapter 14 presentation on fractions. I hope you all enjoyed it or listened to the whole thing and found it useful to you in understanding a little bit about fraction concepts. And I also hope you all have a good rest of your week. Again, thank you for watching, and I hope you all leave replies down below. And yeah, thanks.